Okay, so hello everyone. Welcome back. So today we have the second lecture by Professor Nastase in the series, right? In the first lecture, I think we started about we're starting with general relativity, right? So and then we did Horatiu did the Weber spin reformulation of string of general relativity, and then we went to SUSY, supersymmetry, and then we went to supergravity, and then he showed the 11-dimensional supergravity may blow up at 7 loops, right? So far nobody has done the calculation, right? So if you want to, you can go ahead and do this. I think so far it's been showed till 4th loop that it doesn't blow, right? So 7th loop.
Something like that.
He introduced us to string theory, like starting from Polyakov action, and then we did something, right? So basically he covered something you would have taken at least 4 semester course worth in grad school in just in less than 2 hours, right? So we should thank him.
Yeah.
Summary.
Just a summary, of course.
Thank you so much. Please go ahead. So,
all right. So, can you see my?
Yes.
Yeah.
You may
Okay,
make it full screen.
Full screen. Oh. How do I? Wait. How do I go full screen here? I forgot. Sorry.
I don't see. Menu. No, at the top. Can you see this? Just double click on that.
Where?
On the slide, just double click.
No, it's yeah. I mean, I can make it like this, but this is not. This is just full screen of the
F5.
Left corner, it says menu.
Left top corner menu.
Yeah, but there's nothing.
Oh, okay. It doesn't show us.
Right. I think if you click on menu, there should be some option.
Yeah, there's not.
Shift F should work.
Well,
I think
anyway.
Horatiu, on the bottom right, the third icon from the bottom. Third icon, look at that.
The thing is, I'm already sharing, so yes, that doesn't show. Doesn't show. Anyway. What?
You may convert this into PDF and then open it.
This is PDF, yeah.
PDF, okay.
No.
Todos os para organizar, adicionar salas.
I think if you click on menu.
Yeah, there's no menu here. That's what I'm saying. I'm sure. Well, let me pause share.
Yeah, good. Yeah, sometimes
share.
F11 is it works. Right? So.
Okay, now
just open the PDF.
Yeah. There's no menu anywhere. That is bizarre. View. Full screen. Okay, maybe this is. But now I have to share. Okay. Let's see if it works. No. It's still not sharing full screen. I don't know why. It was full screen before, but now it's not sharing full screen.
Try F11.
F11?
Yes.
No.
Function F11 maybe. Okay, that's all right. If it's not, try to make it as.
That's something else. Well, anyway, Oops. I'll try to. I mean, this is as big as I can get it, but sorry about this.
That's fine. That's all right. You're good. You're good. So.
Oh no, maybe this.
Oh, there you go. That's better.
That's slightly better.
So those are spec.
Okay.
Thank you.
So last time I talked about, as was mentioned here, I talked about supergravity and then string theory. I gave a review of the logic that if we start with just general relativity in perturbation theory, you obtain a non-renormalizable theory, which in principle is not bad if you just want to calculate. It's just very hard to calculate. So at each loop level, you have another term in the action that you need to introduce and a new coefficient. And then supergravity makes it slightly better. You get some cancellations. The maximal 11-dimensional supergravity is apparently renormalizable at low loops, but at 7 loops, a new term can appear. So that's not good either. And then if you want a theory that is at least finite at each loop, that is string theory. That's kind of hard to show, but it's finite at each individual loop level, although in principle it could be divergent when you sum all the loops. So okay, there's an issue there. At least in principle, if you write as a field theory, if you write it like general relativity plus more, then you get an infinite number of terms, the terms that you would introduce if you would just try to normalize general relativity. So that makes sense in perturbation theory. But as I noted, if you try to go beyond perturbation theory, if you want to just have a fundamentally defined quantum gravity theory, then you have a problem because then we still don't know how to define that a priori. We don't have a fundamentally defined, a non-perturbative version of string theory. There's something called M theory, which is defined in certain corners of parameter space, but we don't have a fundamental definition. Now, to find something that goes close to that, we will define the AdS CFT correspondence, which will be a duality relation between strong and weak coupling. And so normally this is used to think of, to calculate things as strong coupling in field theory by using small coupling in gravity. But in principle, one can reverse the logic. And I will try to say something about that. All right, so how do we define AdS CFT? So last time I left with the definition of D-branes, showing that if you consider strings, the theory of strings, then you're invariably led to also fluctuating walls called D-branes, which are endpoints of strings. But if you also consider the low energy limit of string theory, which is supergravity, in supergravity there are solutions that are also extended in space, p-brane solutions. And then in 1995, Polchinski started the so-called second superstring revolution by considering deeply the meaning of the fact that these dp-branes, these endpoints of strings, must be equal with the extremal p-brane solutions of supergravity. He calculated the charges and tensions on both sides, and he shows that dp-branes are these extremal p-brane solutions of supergravity. And then investigating this further, we will be led to AdS CFT. So first, let's understand a little bit what happens when we consider these dp-branes. Well, the open strings can have some factors at n point called Chan-Payton factors. These are basically some indices you can put, some indices I, that label the D-brane. So let me go back to this picture. So I just have several parallel D-branes and I label them by an index I. Then if I have a string extended between a brane I and a brane J, then the string itself would be characterized by these indices Ij, called Chan-Payton factors, right? But then that means that when the D-branes are on top of each other, the massless open string is characterized by these indices I and J, which correspond to an adjoint representation of a UN gauge group. So Ij indices and matrix indices corresponds to the adjoint representation of the UN gauge group. And so you see that the open string, the massless open string state is a vector, but a vector of Yang-Mills theory, in UN Yang-Mills theory. Then you can also calculate the action for the D-brane by the way I said last time, one calculates in string theory something like this, a closed string coming in and colliding with the D-brane and breaking up into an open string that makes the D-brane vibrate. In string theory, this is defined by this diagram in figure B. So one can calculate that and match against the field theory on the D-brane, and one can write the corresponding effective field theory written here. So it's just square root determinant Hij, where Hij is the induced metric. That's the standard thing. This would be just the volume of the world volume of the D-brane. And then to Hij, you add this antisymmetric tensor Bij, and then also Fij, the field strength of the UN gauge group. So Hij is the induced metric, as written here. Bij is an induced B field. There's also some Wess-Zumino term, but I'll not talk about it here. Anyway, so then one can specialize for a 3-brane, so P equal to 3, and consider also a single brane for simplicity. And then even further, go to the low energy limit. And so if you, in this square root, you take alpha prime to 0 and you expand in alpha prime. And the action you get is, you get the Maxwell action, then you get a kinetic action for some scalars corresponding to the coordinates transverse to the dp brane, and then some fermions. If you if you put this together and you look at supersymmetry and things like that, you realize that the action corresponds to the maximally supersymmetric theory that involves spins at most 1, which is N equal 4 super Yang-Mills theory. So N equal 4 super Yang-Mills theory, Yang-Mills, in the case I have N branes, otherwise Maxwell if I have a single brane. And the fields are the gauge field AIA, these X's in here, and some fermions. The actual action, I've written the full action, so including nonlinear terms, I've written it here. And these XM in here were written as the 6 coordinates transverse to the 3+1 dimensional world volume, but they can be recast in terms of the antisymmetric representation of SU4, since SU4 is the same as SO6. And then they appear as these XIJs here. So as I was saying, the bosonic, the simple bosonic version where I just ignore the other fields was just the volume spanned by the world volume of the D-brane as it moves in time. So square root minus determinant of the induced metric. Induced metric being the metric of space-times times these derivatives of the positions in space-time. All right. So the massless fields for the string in here that appeared in here were, well, appeared in here, sorry, oops, were the metric G mu, the B field B mu, and there are other fields as well. And when you count all the other fields, you realize that the fields are the fields of the space-time supergravity multiplet. And that's as it should be. As we said, the low energy of string theory is supposed to be supergravity. But then supergravity itself, you write the action for supergravity and you calculate, you look for solutions of that supergravity, solutions that are similar in, well, the ansatz is similar in logic to the ansatz for, let's say, a monopole. So something with mass in charge. And then you find solutions called p-brane solutions. And among those, the ones that have mass equal to the charge are called extremal. So extremal p-brane solutions. And as we said, the big thing that started the second superstring revolution was the discovery of Polchinski that the p-branes are nothing but the D-branes. So they are the low energy manifestations of the D-branes. So to write the solutions for these p-branes, we think first of the Schwarzschild black hole solution in 4 dimensions. Everybody knows that. It's written in terms of the Newtonian potential, well, with a extra 1 in here, so of a function 1 minus the 1 plus the Newtonian potential minus 2mg over r. And then the Reissner-Nordström solution, the one with mass and charge, is written by adding to the Newtonian potential this extra factor with q squared over r squared. And then the Reissner-Nordström, therefore, is written in a similar way as the Schwarzschild solution, just adding the extra term to the Newtonian potential. In supergravity, what would charge mean? So mass is mass, but of course, what we really want to consider is an infinitely extended p-brane, so the solution that is infinitely extended in the p spatial dimensions. So really, instead of mass, the finite object is really the tension, mass per unit volume. And so that should be equal for the extremal solutions to a certain charge. But charge with respect to what? Well, the charge is the thing that appears in the front of the source for a gauge field. So in Maxwell theory, you would write charge times integral dt A0. But now what we have is so the world volume is not a line anymore, is a p+1 dimensional object, so dp plus 1 psi. So in order to create a source, we have to use a p+1 dimensional antisymmetric tensor, something with p+1 indices and antisymmetric. So the source is A0, 1 up to p+1. Otherwise, for this A0, 1 to p+1, we have the same kind of source, the same kind of solution, the harmonic function, just as for the electron, let's say, given by a charge E coupled to A0, we have A0 being 1 over r. So then, to summarize, the solutions with mass and charge are solutions of the action for supergravity, in which there is a term that generalizes the Maxwell action. You have this, the field strength of this antisymmetric tensor field squared, F squared. And then, of course, now we're talking about supergravity, so you have also the Einstein action and the scalar and some more terms, but these are the relevant ones. But then to this action, we must add the source action in order to get a solution like this, the equivalent of the electron solution. So if we do that, we get the equivalent of the electron solution, which is this p-brane solution written here. Perhaps it looks complicated, but compared to the things that could be in string theory is not. I mean, it's just written in terms of a harmonic function, depending on harmonic function in a transverse 9 minus p dimensions, which is this HP. Yeah, and so everything is written in terms of this HP, right? So this is the extremal solution that has the mass equal to the charge. If I have a smaller charge, let's say if the charge is 0, then I have the equivalent of the Schwarzschild solution with horizon and so on. But the extremal solution is this one. All right. So what does this extremal solution correspond to? Well, extremal solution turns out in supersymmetry, it's something that has a large amount of supersymmetry. So how do we see that? Well, we go back to our simple example for supersymmetry, is the only one that I showed you. The supersymmetry in 2 dimensions and then extended to 4 dimensions. So in 2 dimensions, what we wrote was we had Q with Q. So we had the single commutator for the Wess-Zumino model. If we commuted Q with Q, we get the Poincaré, the translation generator, P mu. And if we generalize this, first of all, we generalize by putting several supersymmetries. Well, the simplest thing could happen is you multiply with a delta ij. If I commute qi with qj. But in 4 dimensions, if I consider that, I can also add some more terms in here, terms that are called central charges because they commute themselves with everything else. But these central charges are actually related to, these central charges are actually related to the charges that are carried by the extremal solutions, extremal solutions of well, supergravity. In the case we have a supersymmetric theory of gravity. But then by considering this 4-dimensional supersymmetry algebra and considering the Wigner method, we know that basically any kind of algebra can be reduced to an algebra of A and the A dagger creation annihilation oscillators. We do this by making combinations of Q1 and Q2 and Q2 bar actually. We get these A and A daggers, and then the 4-dimensional supersymmetry algebra reduces to something like this. So A with A dagger is proportional to M minus Z. B with B dagger is proportional to M plus Z. But since these anti-commutators are positive, that means that the mass must be greater to the absolute value of this central charge Z. That stands for, I mean, I haven't written it here, I should have, but Z is the the single element appearing in this uij and in this case. So this is the so-called BPS bound, that the mass is greater than the charge. And I've written it here for simple supersymmetric theory, but it's similar for supergravity. And so the extremal solution is the one that has mass equal to the charge. And in this case, we see that something special happens. So I get rid of these A's and A daggers, right? So A with A dagger is 0 in this case, if m equal to z. So I'm left with only half of the supersymmetry. And one sees therefore that these solutions will preserve half of the supersymmetry, in the sense that the creation operator A acting on Z, well, more precisely Q, that's a combination of A and A dagger, will give 0 on the vacuum. So this would be a supersymmetric solution, one half supersymmetric solution, more precisely. And when you compute what one half of supersymmetry means, just half the supercharges in 4 dimensions, that corresponds to 4 supersymmetries, and that specifically gives n equal 4 super Yang-Mills. Super Yang-Mills because it's a supersymmetric theory of Yang-Mills, and 4 because this is half of the supersymmetry present in supergravity. And this action of n equal 4 super Yang-Mills looks slightly complicated, but it's actually simple if you realize that this is just the n equal 1 super Yang-Mills in 10 dimensions, which is just the Yang-Mills term plus just a regular Dirac action reduced to the 4 dimensions that we're interested in. And as I said, this n equal 4 super Yang-Mills is obtained on the wall volume of the D-branes, but in this alpha prime to 0 or low energy limit. I mean, I've written here the supersymmetry invariance of super Yang-Mills just to show that, well, yes, it is slightly complicated, but it's not that much so. I mean, we said the simple variation in our simplest model, 2-dimensional Zumino, was delta the phi, the boson is epsilon bar psi, and that's the same thing happening here. Delta of the scalar is epsilon bar psi, just with some indices. Well, the Yang-Mills field is also a boson, and so it also is of the type epsilon bar psi, but also to fix indices, I put a gamma mu in here. And delta psi is the only one that's slightly more complicated. We said before that what we had was d slash phi times epsilon, and that's this term in the middle, gamma mu d mu acting on the scalars, then times the epsilon. But then these other terms come in if you think about it also similarly. So it looks like a complicated theory with some complicated supersymmetry transformation law, but they're not that complicated if you think about it a little bit. So this is the simplest theory that that you can the most supersymmetric one that you can have, and it has therefore a lot of nice properties. In particular, it's a representation of the conformal group. So it's a conformal field theory. It being a representation of the conformal group, it means in particular that the beta function is 0, which means it's scale and scale invariant. It's not only scale invariant, it's actually conformal invariant. in general, there could be non-trivial things happening. So you could have something that's scale invariant and not conformally invariant in some, maybe in some complicated dimensions, but in 4 dimensions, that's not happening. And the fact that we have beta function is 0 and scale invariance implies actually the conformal invariance. An important point that perhaps it's not realized often is that conformal invariance doesn't mean that we don't have quantum corrections. So let's say the conformal dimension, anomalous dimension, delta, right? Just because the beta function is 0 doesn't mean delta is a constant, delta 0, independent of G. No, it actually depends on G in general. So there are no infinities, but there are finite renormalizations. There are no infinities because the beta function is 0, but there are finite renormalizations, meaning delta is not delta 0, but has contributions from the coupling G. All right, so with these preliminaries, let's now get to the definition of the original formulation of AdS CFT given by Nastase in 1997. So, the original AdS CFT is the fact that string theory in a background of of AdS5 cross S5, 10-dimensional background of AdS5 cross S5, is actually equal to N equal 4 superamines with an SUN gauge group. That's the theory obtained at low energy on N D-branes. And this N equal 4 superamines lives at the boundary of AdS5 cross S5. And this equality involves a certain limit that we'll define. So AdS5 cross S5, string theory in AdS5 cross S5 equal to N equal 4 superamines with SUN gauge group. So the heuristical derivation for this, given by Nastase in his original paper, it starts off with the same crucial observation of Polchinski, that D-branes are the same as these extremal p-branes, extremal supersymmetric p-branes. Well, if D-branes are the same as these extremal p-branes, they curve space, right? They are gravitational, and then they correspond to this solution. So this is a particular case of the general solution written in here. The general solution written in here was for an HP with an arbitrary p-brane, but now we're considering p equal to 3. So a 3 plus 1 dimensional world volume, which is what we want for our 4 dimensions. And then for p equal to 3, the solution is given here, as we said, in terms of a harmonic function in the transverse directions to the D-brane. Now there are 6 transverse directions. So the harmonic function is 1 over r to the 4, solution to the Laplacian, right? It's 1 over r to the 4 in 6 dimensions. And the coefficient in here, the numerator of this is r to the 4, where r is a radius. And this r to the 4, excuse me, here's a mistake, r to the 4 equal to this, is 4 pi GSN. GS is the string dimensional coupling, the string theory coupling, that is equal to G Young-Mills squared. So, so GS N is the same as G Young-Mills squared N times alpha prime squared. Alpha prime is the only dimensional parameter of string theory that we talked about. And GSN, in terms of the string theory, is a type of charge, right? N is a number associated with that number, and GSN is the corresponding charge. Okay, so this is the extremal solution. But now let's consider a near extremal case. And remember, I just said that the BPS solution was the extremal solution was a BPS solution saturating the BPS bound, that n is greater or equal to z, or n is greater or equal to the charge. And so near extremal means adding a little bit of delta m, so that n is now slightly bigger than q. And so m is q plus delta m. But now, in the presence of this little delta m, this is what happens is you gain a horizon. You gain a non-trivial horizon, like a Schwarzschild solution, right? Or more precisely, a near extremal Reiner-Nordström solution. But the point is, it's a non-zero horizon surrounding r equal to 0. A horizon, we know that emits Hawking radiation. So we have to, so we can write this process of Hawking radiation in the following way. So from the point of view of the gravitational solution, that is it. We have a black hole, right? Something like a black hole, and with a horizon, and it emits Hawking radiation. That's it. But we said that the extremal p-brane solution is equal to the D-brane, which was described as a wall where strings end. So we have to understand this Hawking radiation from the point of view of these D-branes. And from the point of view of these D-branes, the Hawking radiation is understood like this. So on the D-brane, we have open strings ending. And if we have two open strings ending on the D-brane, then you can collide these two open strings, and they could collide in such a way that they join ends, and then they form a closed string, which is not anymore bound to end on the D-brane, so it can peel off and move into the bulk, right? So that's really the process on the D-brane that gives Hawking radiation, because this closed string, among its massless fields, it has the graviton. So that's Hawking radiation. Okay. All right. So to derive now the AdS CFT, we will consider 2 points of view for this. We will consider 2 points of view for the the fluctuations, the solutions, the perturbations that exist in string theory. So one is in terms of D3 branes, and the second point of view will be in terms of extremal p branes. So let's start with this first point of view, where we consider D3 branes, that is to say, endpoints of strings. So what do we have in the presence of these D3 branes that exist in some place in space-time? Well, we have the open strings on the D3 brane. And we saw that at low energy, meaning when alpha prime goes to 0, expanding in alpha prime the action of the D3 branes, we obtained the n equal 4 super Yang-Mills action. Okay, so we have n equal 4 super Yang-Mills on the D3 brane. That's one set of fluctuations. Another set of fluctuations are the closed string in the bulk. Bulk meaning all of the 10-dimensional space-time. These are the zero modes, the massless modes, which are given by supergravity, as we said, plus all the infinite tower of massive modes of the string. But if we are interested in the low energy theory, like in the first line, we're interested in low energy theory given by alpha prime goes to 0. The massive modes of string all have masses of 1 over alpha prime, so become infinitely massive when alpha prime goes to 0. So at low energy, we get just the supergravity modes. All right. And finally, we have interactions between these open strings and the closed strings, giving, for instance, the Hawking radiation that we described. So we have the open strings on the D3 branes and the closed strings moving away. And there's the interaction giving the Hawking radiation. Now, in the alpha prime goes to 0 limit, the bulk action, the action for these bulk modes, becomes the supergravity action. We said that. And the brane action becomes n equal 4 span-mills. We also said that. But the interaction between them is proportional to the Newton's constant, because we said this gives Hawking radiation. And the Newton's constant is proportional, you can realize that is proportional to the G string, to the string coupling. I mean, that's kind of natural, it's the only coupling present in string theory. And then by dimensional reasons, it's also proportional to alpha prime squared, because this has dimension minus 4, excuse me. So it has to be proportional to alpha prime squared. This is Newton constant in 10 dimensions, right? Kappa Newton in 10 dimensions. So 16 pi G Newton is equal to 2 kappa Newton squared. So this has dimension minus 4. So G Newton has dimension minus 8. In 10 dimensions, that's correct. But we are interested in the alpha prime goes to 0 limit, we said. That's the low energy limit. So kappa Newton goes to 0. But if kappa Newton goes to 0, the gravity is also free. So the supergravity modes here are free. So what we get is actually, in this point of view, we get free gravity in the bulk and n equal 4 span-mills on the D3 branes. One important observation is that, we will see, oh, why did I put it here? Sorry, this it should have been in the second point of view. But anyway, so I'll say it now and repeat it later. So we'll see that we'll obtain AdS 5 cross S5. And we'll obtain AdS 5 cross S5 in this alpha prime goes to 0 limit. But the boundary of AdS 5 cross S5 is actually 4-dimensional. Is you can think of it as S3 cross R, or making a transformation to the R3, 1 to just 4-dimensional flat space. And the point is that when you go to the boundary of AdS 5, S5 shrinks to 0. So although it's a 10-dimensional space, its boundary is 4-dimensional. So that will match with the 4 dimensions on the D3 brane. Okay, so the second point of view. Instead of D3 branes, I consider just the supergravity solutions, the extremal p-branes. The geometry has then 2 asymptotic regions. In the R going to 0 limit, so one looks at this solution, the extremal p-brane solution, and you consider R goes to 0. And then in the harmonic function, for instance, the 1 is negligible, and we're left with capital R4 over little r4. And then the metric one obtains is the metric of AdS 5 cross S5 for R goes to 0. On the other hand, for R goes to infinity, looking again here, for R goes to infinity, this extra term is negligible, and we're left with the harmonic function being 1. That is, just drop it. And then metric is just dx squared plus dr squared plus r squared d omega 5 squared, so flat 10-dimensional space. So we have these two asymptotic limits. R goes to 0, which is actually an infinitely long throat. Remember, general relativity is funny, so you might say it's R going to 0, so therefore an infinitesimal region, but it's actually not. It's actually an infinitely long region if you study the geometry properly. And R going to infinity is just flat space-time. Okay, so what do we obtain in these two asymptotic regions, R going to 0, R going to infinity? Let's see. So first of all, let's understand the relation of between the energy felt at the point R and the energy felt at infinity, at R going to infinity. The energy felt at the point R is described by the generator dd tau. And tau is dt times square root minus g00. But ddt is the energy felt at infinity, where g00 is just 1. So, well, minus 1, sorry. And so ddt is the same as E infinity. So E infinity, reversing this, is square root minus g00, which is h2 minus a quarter, times ER. And h2 minus a quarter in this R going to 0 limit is proportional to R. So this E infinity is proportional to R ER. Okay. So now let's consider a fixed ER, a fixed energy of this infinitely long throat. And then when R goes to 0, that means that the energy at infinity goes to 0, which is another way of saying that we're considering low energy excitations only. On the other hand, at R goes to infinity, we have also variations of R going to infinity, long distance. And variations of R going to infinity is the same as low energy. Energy goes to 0. And the gravitational coupling has negative mass dimensions, so the effective or dimensionless coupling for gravity is g Newton times e to the power d minus 2. So when e goes to 0, this goes to 0. That means gravity is free. So at infinity, we have again free gravity in the bulk, just like in point of view number 1, we had free gravity in the bulk. So comparing the point of view number 1 with point of view number 2, we see that we have two asymptotic regions with different kind of fluctuations, but one of these is the same, free gravity in the bulk, which means if the 2 points of view are the same, that the other one must also be the same. And in point of view number 1, we obtain 4-dimensional N equal 4 super Mills with SUN gauge field living on the D3. And on the other point of view, we obtain the gravity modes in the R going to 0 limit, in the D-brane background, and also for alpha prime goes to 0. And if I take R going to 0, I obtain this AdS5 cross S5 metric. And then if I am even better, even more careful about the limit, and I consider that what is fixed is not, energy has dimensions. So we have to, when you say something is fixed, it's better to consider a dimensionless number fixed. So we said ER is fixed, but it actually should be ER in the units of string theory, in units of square root alpha prime. So ER times square root alpha prime. And also consider the energy at infinity fixed, then E at infinity over ER square root alpha prime is actually equal to, so before we said was equal to R, but now when putting the dimensions correctly, we see that it's R over alpha prime. So R over alpha prime is now called this U, and it's fixed. And so the metric becomes this AdS5 cross S5 metric written here, with a radius of AdS5 given by this formula. R squared is square root 4 pi GSN. R squared over alpha prime is equal to this. Yeah. All right. So we obtain that n equal 4 supermills in 4 dimensions on the D3 is equal to this AdS5 cross S5 metric written here in terms of an U factor, of an U variable or coordinate. So one slightly odd thing is that one side is 4-dimensional, the other side is 10-dimensional. But we said the explanation for that was that the boundary of the 10-dimensional AdS5 cross S5 is, if we consider global coordinates for AdS5, we get S3 cross R, and otherwise for Poincaré AdS5, we get flat R3 cross 1, R3, 1. But the point is that at the boundary of AdS5 cross S5, S5 shrinks to 0. Now, this phrase refers to calculating the calculating the Penrose diagram of AdS5 cross S5 and seeing what happens at the boundary. So it's a perfectly well-defined statement. So the boundary of the AdS5 cross S5 gravitational side is a 4-dimensional flat space where we have this n equal 4 super Young Mills with SUN gauge field. So just a little bit to understand a little bit better about Penrose diagrams. Perhaps it's not very much discussed in general relativity courses, although it should be. So Penrose diagrams are a way of representing a complicated gravitational space in such a way as to bring the infinity to a finite distance, so we can draw it on a piece of paper, and also keeping causality, keeping the relations of causality, meaning keeping light rays at 45 degrees. And one can calculate the Penrose diagram. It's not it's not really algorithmic, but close enough, so one can calculate it for any given space. And for 2-dimensional Minkowski space, the simplest thing you could imagine is this square in when time goes upwards and space goes horizontally. Well, diamond rather, right? The rotated square. Then if I go to 3-dimensional or higher Minkowski space, I have a triangle, but I have to, it's a figure of revolution. So I have, instead of a single horizontal spatial dimension, I have several. So then I have to rotate the triangle around the time axis and obtain a figure of revolution. For AdS5, well, for AdS2, let's say, the Penrose diagram is like this. So if we consider the Poincaré patch, one obtains also a triangle. And if we consider the global AdS2, so two-dimensional anti-de Sitter space, then we consider a strip in between -π/2 and +π/2 in this spatial theta coordinate, and otherwise running infinitely in the time direction. So I said we have to bring infinity to a finite distance away, but as much as possible. So usually space infinity should be brought to a finite distance away, and time maybe cannot be. So I've emphasized the Poincaré patch, which is this triangle on the global AdS space-time. Sometimes the global AdS space is also called the universal cover of AdS space, to emphasize that it's a bigger space than the Poincaré patch. Now, if I do the Penrose diagram of AdS with a dimension greater than 2, basically what I have is I have a figure of revolution, because I don't have just one horizontal coordinate, I have several. So then I rotate this strip around the time direction, and I get a cylinder. By this figure of revolution, I get a cylinder. So AdS5 in particular, the Poincaré diagram, the Penrose diagram, excuse me, is a cylinder. And so, I mean, a full cylinder. Yeah, I forget if there's a mathematical name for it, but so the boundary of it is then the surface of the cylinder, which is a sphere cross time. So let's understand a little bit better about what happens to anti-de Sitter space. So anti-de Sitter space is obtained by writing a flat embedding metric, and then an embedding condition similar to the one for the sphere, just with some extra minus signs. So it's embedded in a space in a metric with 2 minus signs, so 2 time-like directions, and the embedding condition has corresponding minus signs in the same places, but also a minus sign in front of r². And but otherwise, this is just some double big rotation of the sphere, right? So we can see then that both the metric and the embedding constraint are explicitly invariant under SO d-1, 2 by construction. And we can also calculate that the Ricci scalar is negative for this space, so it's a space of negative curvature. So the Poincaré coordinates for the Poincaré patch of AdS give this formula for the metric. So it's r² over x0², conformal factor, and then a d-dimensional flat Minkowski metric. So because of it's only when writing a Penrose diagram, I ignore conformal factors. So because this is up to a conformal factor the same as flat space, the Penrose diagram is the same, right? That's why we said that the Penrose diagram of the Poincaré patch was just a triangle. One can write this the conformal factor or warp factor, can make it explicit and exponential in this way. This is the form used in the Randall-Sundrum model, for instance. One observation is that even though the coordinates are infinite in extent, the space is not complete in the sense that I can reach infinity in a finite time by going with the null ray, which is supposed to be fastest, right? So in this form, I write this ds squared equal to 0, and I get that t is finite. So that means that one of the things that this means is that the Poincare patch is not enough. One had to extend it to the universal cover or AdS in global coordinates. And that's written again by some Wick rotation, double Wick rotation of a sphere. Well, some Wick rotation of the sphere. I've written here the metric of the sphere and here the metric of AdS. And finally, there is another coordinate transformation that makes it up to a conformal factor, the same as a cylinder, which is the Penrose diagram I argued for. So I argued for the Penrose diagram of being a cylinder in here. That's a figure of a revolution obtained by rotating this strip. And in this strip, there's a triangle corresponding to the Poincare patch. So the boundary of the cylinder is still reached by light ray in a finite time, but then it's reflected back and it goes in zigzag. So it goes to the so-called infinity, the boundary, and then goes back inside. Which means that AdS is somewhat like a finite box with a boundary. That in the sense that light ray reaches its boundary in a finite time. And that is at the heart of how can it be that we have this holographic story, that there's a theory, gravitational theory in AdS that is equivalent to a field theory on its boundary. Well, it can be so because the boundary, unlike flat Minkowski metric, it can be reached in finite time. So we can project anything that we do inside AdS onto the boundary. All right, so let's see now a little bit of what AdS CFT corresponds to. Well, the limit is alpha prime goes to 0, GS goes to 0. Part of it was that. And what one obtains is actually, so GS was equal to G squared Yang-Mills. And GS or G squared Yang-Mills goes to 0 and N goes to infinity, but in such a way that lambda, their product, G Yang-Mills squared N, is fixed. That is the large N limit of 't Hooft, in which 't Hooft showed, this is just from the 't Hooft paper, that the amplitude for gauge theory is proportional to this overall factor, G squared N to the number of loops times N to 1 minus 2 times H, number of handles of the diagram. So I've written here for you two diagrams that don't have any handles, A and B, and C, a diagram that has a handle. It's a non-planar diagram, but as you can see, this vertical line looks like a handle, an extra handle on a piece of sheet, right? So that's what this means. This has an extra H equal to 1. So an extra 1 over N squared, this diagram C. Whereas for the other diagrams, the effective loop counting parameter is lambda G squared Yang-Mills times N and not just G squared Yang-Mills. But the difference is that now the difference from the usual 't Hooft limit is that lambda is fixed and large, usually Hopf thought about the limit where this was the theory was still perturbative Yang-Mills with small lambda. So in this case, we have a non-perturbative quantum field theory. And what is the map between the field theory and the gravitational theory? Well, in n=4 Sperr-Mills, in the field theory, we have operators O with some conformal dimension in some representations. And they correspond to some fields in AdS5 of some mass and some representation. And so the relation is between mass of the field in AdS5 and dimension of the operator in Super Yang-Mills, and the relation is given here. Further, Witten considered the relation to the relation between observables in Super Yang-Mills and observables in gravity. So to understand that, we consider on-shell fields in AdS5, so satisfying box phi equals 0. Then phi goes like one finds that phi goes like the x0, the radial coordinate, to the power the dimension of the dual operator, or d minus delta, and then times a constant. And that constant, well, one of them at least, the one of the leading term, can be identified with a source for a dual operator. So what does that mean? Well, if you think about it, the basic object in a field theory, as in a string theory, is a partition function. So on the boundary, we'll consider the partition function for these operators with a source. And so something like a path integral over E minus the Super Yang-Mills action plus the integral of an operator times the source for it. And the fundamental idea of Witten now sounds stupidly simple afterwards, after he said it, that what the duality means is that the partition function on one side equals the partition function on the other. So Z on the boundary is equal to Z in the bulk. Z on the boundary is this one, and Z on the bulk is the string action with a source phi 0. But phi 0, remember, is a source on the boundary, right? It's a source on the boundary of AdS5. And in our limit, the string becomes just classical supergravity. So the partition function for the string becomes just, and moreover, so it's supergravity and it's classical. So there's no path integral anymore, it's just classical. So that's just E minus the action without any path integral in front. And supergravity, not strings. So E minus S supergravity, depending on fields that have a boundary source phi 0. And so equating the two sides, we have that this partition function of operators in the CFT is equal to E minus supergravity action. And then let's say correlators in field theory, which are basic object we kind of use in field theory, are obtained by derivations of the partition functions. And so to obtain them in any regime, including the non-perturbative one, now we substitute the supergravity partition function, which is E minus S supergravity, and we're getting the result for these correlators. Not surprisingly, the correlators, the perturbative correlators for the 't Hooft coupling G squared Yang-Mills N goes to 0, would match the values for the non-perturbative the non-perturbative values that are obtained via AdS CFT from the classical supergravity only if there is some supersymmetry argument. Otherwise, they are different in principle. Otherwise, there's some function of this Hopf coupling that interpolates between the lambda equal to 0 and lambda equal infinity regimes, right? So at the beginning of AdS CFT, there were lots of tests of correlators. I wrote the paper myself for such thing, a 3-point function of R currents in momentum space. And we found agreement, but the agreement, although it looked impressive, on a second thought, it was more due to supersymmetry than due to something else, because otherwise it should have been in principle a function, interpolating function of lambda in between. There's one exception to this that is kind of nice. Anomalies. Anomalies in quantum field theory, we know that they come only from one-loop diagrams. Gauge anomalies come from one-loop diagrams, from the triangle diagram written here. Right? So so one can calculate then the anomaly of, so the anomaly in the 3-point correlator of currents in n equal 4 supermills and gets this result. And the nice thing is that this matches completely the result from supergravity, where the anomaly is matched by another interesting thing in supergravity, namely a Chern-Simons term that appears in terms of the gauge fields. The gauge fields written here is green, being the sources for the currents of supermills. Okay, all right. So we have at least one example of matching, but then as people started matching more and more things, there came people started realizing that AdS CFT is valid not only in this particular limit of GS goes to 0 and alpha prime goes to 0 that was done in the original paper of Maldaceno, but the equality is valid at all couplings. So then it becomes, in principle, possible to think about calculating things at finite coupling and still have matching between both sides. Okay, let me then look at one other example, which is of an observable, which is the Wilson loop. The Wilson loop is in field theory is considered, in QCD in particular, is when one considered very heavy quarks. So a quark and an antiquark, like written this in figure A. So they're very heavy, then they move just on a straight line in time. And we can just you can just put an extra connecting line in the far future, in the far past, and make this rectangle. And then define this Wilson loop as the trace of the path order exponential of integral a mu dx mu along this closed contour. And then this object is gauge invariant. So we have a gauge invariant object, the Wilson loop. This is a very important thing. So we can define, it's shown that we can calculate basically any observable in a gauge theory by operations on various types of Wilson loops, which are gauge invariant things. So any observable can be obtained in principle from Wilson loops. So this is a very powerful object. Well, this has been usually used mostly to calculate the quark-antiquark potential,
Because if we consider this particular rectangular contour in figure B with a very long rectangle with a small distance r in between the two lines and a very large time direction t, then the VEV of the Wilson loop is proportional to E minus the quark-antiquark potential times T. And then this allowed one to consider confining potentials, which are potentials that are linear in the distance. So in QCD, one thinks that this is what happens at large enough at a particular distance, because then there's a QCD string, namely a flux tube of constant cross-section being extending between the quark and an antiquark. All right, so this is all you know, just to see why this is useful, but this is not what I want to show. I want to show that this VEV of the Wilson loop in general can be obtained from the partition function of the string with a boundary condition. So the VEV of W, this is now the same logic as Witten's original logic, equating partition functions. So the VEV of this Wilson loop is in some sense a partition function, and then that partition function must be equal to the partition function of the string with a given boundary condition for the string, for the endpoints of the string, which is just E minus the string action with that boundary condition. Well, there's a subtlety that really the Wilson loop one calculates this way is not the normal Wilson loop, but just a generalized supersymmetric Wilson loop with some extra terms. I don't want to get into that because it's not really relevant for my points. But what I want to say is that this Wilson loop now, because AdS CFT is defined at all couplings, is a good observable at any coupling. And now comes the example I wanted to give you to come back to the subject of these lectures, quantum gravity. If I consider instead of this standard rectangular contour used for the quark-antiquark potential, if I instead consider a circular contour, then this can be calculated exactly. Now, at small taut coupling, we can just calculate it using Feynman diagrams, the usual thing. However, it turns out that we can also calculate this exactly at any lambda using a variety of modern techniques involving matrix models or supersymmetric localization, all of which are actually field theory techniques. So this has been calculated both at n going to infinity and even at finite n. So the result at finite n and finite coupling is given here by some Laguerre polynomial. And the result at n goes to infinity is given by some Bessel function I1. And one can expand this result at small coupling and large coupling and find these results. So the small coupling stuff, you can calculate it with some Feynman diagrams easily. The large coupling result could in principle be calculated from a string, right? And now on the string side, then this partition function for the string that we've calculated using exactly this Wilson loop VEV is a good quantum gravity observable, right? This is a partition function on the condition on the. So the only thing we need is that there's a fixed boundary for the
fluctuating space-time in the bulk. It has a fixed boundary, and on this fixed boundary, we have a boundary condition for the string. That's the only thing needed. Otherwise, this makes sense in principle, even in a non-perturbative quantum gravity theory. And this is calculated exactly. So is correct, which is proven by many calculations. You can define this to say, well, I've calculated something in quantum gravity. And just to see how you just get away a little bit away from classical strings, well, if we consider 1 over lambda corrections, these correspond to alpha prime corrections for the string. Alpha prime, remember, is the coefficient, the unique dimensional parameter of string theory. And so these quantum fluctuations of the strings, I have a string ending on some boundary condition, and then I just let it fluctuate a little bit instead of be just classical. On the other hand, G string corrections, these are quantum string corrections. So this means the string world sheet now can make loops, changing its topology. So we can, in principle, calculate these small corrections. But in the end, this quantum gravity observable is defined and calculated from supermills at any coupling, any alpha prime, any GS, so any quantum gravity strength. The final example I want to give for you of something relevant to quantum gravity is the example of finite temperature calculation. At finite temperature, Witten showed that the metric for AdS at finite temperature, given by a certain limit of the AdS black hole, is written here. So it's written, it looks like, so it is actually AdS 5 crosses 5 in Poincare coordinates with the extra function f of z, which is this particular harmonic function with a minus sign in it, like for Schwarzschild. And the temperature of this associated with this solution is 1 over pi z0. Now, so this is a kind of black hole with a horizon. So one can calculate the Bekenstein-Hawking entropy, just the area divided by 4g Newton. And then you have to think that the entropy really counts the number of effective degrees of freedom. Now, what we're used to it in the semi-classical calculation of Bekenstein and Hawking. And the essential point of the Bekenstein-Hawking entropy is that this is a holographic quantity, right? It's proportional to the area of the horizon of the black hole and not its volume. Which is how Toft and Susskind originally thought of the holographic idea, that quantum gravity should always be holographic. But now this entropy should equal the entropy of the dual quantum field theory, n equal 4 supermills at finite temperature. Now, if you look at this black hole, you see there's this dy squared in here. So the area is infinite because you integrate over this dy squared. So you have to define the entropy density by dividing by these 3 coordinates. That's fine. That's what you do in field theory anyway, everywhere. And you obtain this result, r cubed over 4g Newton in 5 dimensions times z0 cubed. Then you can calculate G Newton in 5 dimensions. Well, I've written there the steps, that doesn't matter. And Z0 was related to the temperature, so temperature was 1/pi Z0. So we obtain that the entropy density, which in field theory is entropy density at lambda of coupling infinity, is proportional to n squared with constant, with n squared and t cubed. T cubed is dimensional analysis, but n squared is interesting, and pi squared over 2 is, moreover, a coefficient that is very important. You can get, once you get the entropy density by thermodynamics, you can obtain the pressure and energy density as well. But let me instead look at weak coupling now, so lambda equal to 0. At weak coupling, I have n equal 4 super mils, which is a bunch of fields, 3 fields if lambda equal to 0. And then I can just count the entropy. So we know that the free bosonic degree of freedom has 2 pi squared t over 45, t cubed, sorry, t cubed, not t, over 45. And one free fermionic degree of freedom has 7/8 of that. And then counting the degrees of freedom, there's actually n squared minus 1 for the adjoint of SUN. There's 8 bosonic degrees of freedom, 8 boson fermionic degrees of freedom, all in the adjoint. Multiply all these factors together, we get again n squared t cubed, but now with 2 pi squared over 3 coefficient. So then the ratio of the entropy calculated from gravity, from Bekenstein-Hawking, so at lambda infinity, and the entropy at 0 coupling from free super mils is 3/4. And from thermodynamics relations, we can obtain that the same result is true for pressures and energy densities. But this result, 3/4, is interesting. So first of all, in lattice QCD, which is not super mils, but it's still a field theory. In lattice QCD, one finds about an 80% reduction from lambda equals 0, which in QCD corresponds to ultraviolet, and lambda equal infinity, which in QCD corresponds to infrared, right? So zero coupling is UV for QCD. So 80% reduction instead of this 75% reduction for super mils. But in any case, it's a reduction. And that, in a field theory like QCD, is consistent with the reduction of the effective degrees of freedom along the RG flow, right? When you go from UV to IR, you do this Kadanoff blocking, where you just average over bigger and bigger regions. So as a result, you always are supposed to get less or at most equal number of degrees of freedom. So that makes sense. But now what I wanted was to talk about quantum gravity. So now I reverse the logic, and I just want to describe this in gravity. So now the semi-classical result, the Bekenstein-Hawking result, A horizon over 4, G Newton, goes to the strongly coupled quantum gravity result, which is the free super mils by AdS CFT. And that's just a factor of 4/3, right? So in quantum gravity, we have, in some sense, an increase of the entropy density or effective number of degrees of freedom from semi-classical to strongly quantum. So we have at least at least a simple calculation that, assuming AdS CFT is valid, tells us something about quantum gravity. Now, there are many other observables that have been computed in AdS CFT. However, there are not many that have some simple understanding in terms of quantum gravity. That's why I chose these particular ones. I chose the Wilson loop, and first the anomaly, then the Wilson loop, and finally the entropy density. So the big essential assumption is the existence of AdS CFT, but once that is assumed, since it has been tested many times, then we can really say something useful about quantum gravity. So that's everything for today. Thank you.
Thank you so much, Horatiu. So there is a question in the chat. So would you like to make the question? Would you like to ask the question?
Oh, I see here. So in the Penrose diagram in E form, can we compare it as Kaluza-Klein theory? Let me go there. Not sure what that was. Oops. What did I? I guess this is it, right? So this was for AdS 5, right? So indeed, as I was saying, the theory that you have is AdS 5 process 5, right? So, but I was also pointing out, I wrote it here, though it should have been probably later, very important observation that the boundary, so the boundary of AdS 5 process 5, and this means when following the steps of the Penrose diagram, right? The boundary of AdS 5 process 5 is just the boundary of AdS 5, because when following the steps of the Penrose diagram and getting rid of conformal factors, one sees that S5 shrinks to 0 side, right? So it's not even an issue of Kaluza-Klein. Well, you can say it's Kaluza-Klein in some sense, yes, but where the reduction is exact, right? In the sense that there's nothing else at the boundary.
Great. So any other questions, guys? So anyway, we will be posting this lecture, right? So you can watch the lecture again at your leisure and then ask the questions next time, right? So, I think Alicia has a question. Go ahead.
Can you hear me?
Yeah.
Okay. Yeah, so, well, two questions. So first, you made an observation that the action that you get for n equals 4 super young meals in 4 dimensions, even though it looks kind of difficult, it's just like the dimensional reduction of the 10-dimensional supergravity action, right? So
super young meals, 10-dimensional
super young meals. So is it usually, I mean, is this a general scenario, or is it just like you said, just an observation in this case, in these certain limits of the theory?
Well, in this case, it was a given simply because, as I was saying, n equals 4 super meals is the unique action with at most. The unique action with maximal supersymmetry for at most spin 1, right? So if I consider only scalars, fermions, and vectors, the maximal supersymmetry I can have is n equals 4 in 4 dimensions. And n equals 4 in 4 dimensions corresponds to n equals 1 in 10. So there's a uniqueness situation. So because of that, it was obvious that this should be the case. In general, it's not. If you have smaller supersymmetry is not. Well, there's an interesting story if you believe, I mean, within supergravity, even, I mean, more than in super young males, within supergravity, whether you have some complicated lower supergravity theory, can it be obtained from Kaluza-Klein reduction? And I don't think there's a general there's no general story about that. It's just a guess. Sometimes it works, sometimes not. But in this case, it was obvious simply because of the supersymmetry was maximal. So.
Okay, great. Yeah. So, and you also made a comment about this Wilson loop, or the expectation value of the Wilson loop, being a very unobservable in quantum gravity. Is this in what dimension would it be unobservable of quantum gravity? Because at the end you have in 10 dimensions.
Yes, yes.
Because yeah, when it's good that you have this slide now, because you made the argument from point of view number 1 and number 2 that actually both of them in 10 dimensions, you have this limit of where you have just Minkowski in 10 dimensions, right? So yeah, I'm having trouble like finding a compatibility between having these Minkowski 10 dimensions and these non-perturbative observables.
Right. So again, the same answer I gave to the previous question, to the question from the chat, right? So the essential, very important point is this: that the boundary of AdS5 cross S5 is although it looks strange, so you normally say the boundary has only 1 less dimension, but in this case, no, the boundary has 6 less dimensions, right? The boundary is 4-dimensional. And that's simply because when you look at the boundary, the S5 shrinks to 0, right? So so the boundary is actually 4-dimensional. So holography in this case means that you have a 10-dimensional theory projected onto its 4-dimensional boundary. Okay. So that, yeah, that's so people usually say about say things about AdS5, and in some sense it's fine, because AdS5 itself is the boundary of AdS5 is 4-dimensional, and that sounds you know, more easy to understand. So and it's fine because in AdS5 you could make Kaluza-Klein expansion, not reduction, on you know, AdS5 and S5 has the same have the same radius, so you cannot say that you reduce on S5. You can only say that you make an expansion on S5. But when you go at the boundary, then at the boundary it's a 4-dimensional theory. So this whole 10-dimensional theory, which, if you want, you can think of it as Kaluza-Klein expansion. You know, the Kaluza-Klein expansion is nothing but a mathematical trick. It's just writing a 10-dimensional theory into 5 dimensions, right? It's just generalization of Fourier expansion, right? It's just a trivial identity. It's okay, you can say it's 5-dimensional theory, but it's really 5-dimensional theory of an infinite set of fields, which means really a 10-dimensional theory. So so this 10-dimensional theory is really equal to the 4-dimensional theory at the boundary, right? So that's
yes, thank you. Like, this clarifies it a lot.
thanks. You're mute. You're mute.
Okay, sorry. Thank you for noticing that. Okay, any other questions? Okay, if not, maybe I'll ask a couple of questions. Again, related to the observables. You said the partition function being observable. You mean we can calculate the observable quantities using partition function? or the partition function by itself is observable?
Well, it depends on what you refer to. So what partition function you consider, right? So the partition. So there are two examples I considered. The example of Witten was partition functions with sources on the boundary, right? That's kind of the natural thing from the quantum field theory point of view, right? So this this ZO, the partition function for some operator, and then I put a source for that operator. That's natural from the point of view of field theory, a natural observable from point of view of field theory, because from it you derive in this way all the correlators. And then you can rewrite this as some partition function in string theory. But with respect to the Wilson loop, I was saying that this is something that makes more sense. Sorry, where did I write it? Yeah, so I said from the point of view of string theory, this is something that makes more sense. You know, in string theory, perhaps in string theory, in the sense that there it's well, something that could be well, I'm not sure how you would observe it in quantum gravity. That's the point. That's the point that everybody will ask. You know, in any quantum gravity model, how do you observe some observable? But I'm saying, at least logically, it makes sense that I have a partition function with a fixed boundary conditions if I define that the boundary is fixed, and then I let fluctuate all in the middle, but the boundary is all fixed. The principle should be a well-defined observable in quantum gravity, although, yeah, how you would define it? I mean, you would still need to go somehow to the boundary. So, yeah, I don't know.
Another question is regarding the anomalies, how they match. I think a couple of slides.
Yeah.
So, see, as you clearly mentioned, so anomalies appear, the triangular anomaly, right? So it appears in one loop diagrams, and we do loop things when we are doing perturbative calculations. But this AdS CFT business is the non-perturbative thing, right? So where is the...
No, but that's the beautiful thing about anomalies, right? That they are valid in a non-perturbative theory, right?
Yes.
So you have, in particular, you have the post-anomaly matching conditions, which are very important conditions for phenomenology in the case that you want to match UV and IR, and IR is a strong coupling, right? So the point about the anomaly is that they are one loop exact, not perturbatively exact. Perturbative and non-perturbative, right? So that they are, yeah. So that's really the answer. That you know, it sounds like you're doing a perturbative calculation, but actually you're not. You're doing a full non-perturbative result. And yeah, in classical gravity, you have this Chern-Simons coupling, which again somehow, so that part I don't quite understand why this would not be renormalized, not only perturbative but not even non-perturbatively in quantum gravity, right? That's basically the argument to say that this is so perturbatively perhaps I can understand, but non-perturbatively it's harder to. But once you accept that, yeah, you have a matching that is valid at any coupling.
Fantastic. That's really great. Thank you so much for the lecture, Horatiu. If anybody else has any questions, may I ask now? Okay, looks like there is one more. do we have any lecture about quantum entanglement in the near future? Yes, I think we will have some. I think we will notify everybody about that. Okay. So, and regarding the lecture today and from the last week, I think they will be posted very soon on the YouTube. And the next lecture will be on October 19th, right? So that's 2 weeks from now, 3 weeks from now. Yeah, it's 3 weeks from now. Is that correct? So either way, you'll all receive a notification by email with the Zoom link, right? So see you all next week. Thank you so much once again, Horatiu. See you in 3 weeks. Okay.
Thanks. Bye.
Bye-bye. Bye-bye.